Ladies and gentlemen, the last and the fourth paper, the effect of heat treatment on the electrical and structural property of activated cotton fibers. This is also a joint paper. Dr. m.nasr, B.I.D., M. Ellison, School of Material Sciences and Engineering, Clemson University, but Dr. Nasr is currently working for the National Research Center of Egypt. Please welcome Dr. Nasr.
Thank you, Mr. Chairman. Thank you all for attendance. Now allow me to switch gears a little bit to a different subject, which is the effect of heat treatment on the... You hear me very well without the mic?
We need a mic.
We need a mic. The subject today is about the effect of heat treatment on the structural and electrical and structural properties of activated carbon fiber. In the beginning, let me introduce to you what is the activated carbon fiber, the content of the topic. I'm going to talk briefly about the preparation properties and application of ACF, which is the activated carbon fiber. I'm going to talk about the objective, experimental, result and discussion, and finally the conclusion and reference. In the beginning, let me introduce to you the activated carbon fiber, which is exactly like the regular carbon fiber, except we have an additional step, which is the activation step. What I mean by activation, activation is a controlled oxidation of the surface of the carbon fiber. We do the activation using a mixture of carbon dioxide with steam. And during this step, we impart the important properties of ACF, which is the high surface area, as well as we create a surface group on the surface, and mainly it's an oxygen functional group, such as the hydroxyl, carboxyl, ketone, as well as aldehyde and ester. The activation step change, like I said, the structure, the surface structure of the carbon fiber and transfer it to the active carbon fiber. The activation creates a huge surface area, and it can reach it up to 3,000 meters square per gram of the fiber, which is huge, of course, and this is the importance of the activated carbon fiber. Also, because of the activation, we create three different types of pools. We create the micropores, which is less than 2 nanometers in size. We create meso pools, which is above 2 nanometers and less than 50 nanometers. And also we create the macropore, which is higher than 50 nanometers. Also, due to the oxidation step, we cannot completely gravitize the activated carbon fiber like in regular carbon fiber, because regular carbon fiber is long graphitic layer and the crystallinity is well developed. Here we break the crystallinity into small crystallites due to, of course, to the activation. We found also that treated the ACF at higher degree, which up to more than 1500 degrees, the micropores start to collapse and the shape of the fiber starts to change. Next one, please. One of the most important criteria also of the activated carbon fiber is the electrical properties. The regular carbon fiber is very well conducted because, like I said, it's more crystalline and it is very well developed, the crystallite layer. But here we have small crystallite, so now the electrons, which is a charge carrier in this case, has to hop or to move from one crystallite to another, and that's why the conductivity in activated carbon fiber is less than the regular carbon fiber. Of course, the boundary between the crystallite can obstruct the charge carrier. Also, due to the high surface area, even in the room temperature, the activated carbon fiber can absorb moisture, gases, everything, and of course it's going to go into the pool and may increase the barrier of the electron. Next one, please. And here is the mechanism of conduction. And here we can represent the small crystallite in the ACF by these small circles. And now here is the electron can hop between on the boundary and into another crystallite. Because, like I said, here this is considered to be a core due to the activation. And with increasing the temperature of carbonization and graphitization, the graphitic layers start to grow a little bit and become more easier for the electrons to move between the ACF crystallite. Due to these properties of ACF, ACF started to be a very good candidate in different applications, such as the environmental one, of course, high surface area. We need to get use of that using by making water and gas filters in the purification, protective clothing. It can absorb any materials into it, gases and gas masses. Also in medical, such as in blood and artificial kidney filters. It can be used as a catalyst and catalyst support because it has high surface area as well as a good amount of conductivity. So you can do some sedation reduction reaction into the surface of ACF. And one of the up-to-date application of ACF is in the electrical application. Electrical application, we need to get use of the high surface area and also the amount of conductivity ACF has. So we can use now the ACF as electrode material in the energy storage devices because you can imagine we need a high density, a high energy density, and lightweight and small size. And all of that can be found in the ACF because the high surface area, lightweight, and also it has a good mechanical properties. So we can use it as an electrode in the fuel cells, lithium rechargeable batteries, and supercapacitors. So the objective of this study is to prepare ACF material with enhanced electrical properties. What I mean by enhancement in the electrical properties is, like I said, it has a less conductivity than the regular carbon fiber due to the breakage of the crystallite. The second objective is to maintain the high surface area. I don't need to fix the conductivity and lose the high surface area, of course, of the ACF. So I need to compromise between these two items. So we're going to take the thermal treatment as a tool and study how it affects these two properties. Next one. So the experiment, we used a band-based activated carbon fiber, and we did the thermal treatment in 300, 600, and 900 degrees C in, of course, a controlled atmosphere. And we measured the current voltage characterization, current time relationship, surface area, and pore volume analysis. Also, to follow up the structure changes, we did scanning electron microscopy as well as the X-ray diffraction. Now let us see the first data we have. We measured the current voltage relationship. Actually, we put the fabric, the piece of a fabric, between two electrodes, and we apply the voltage between between 0.5 and 4 volts, and we measure the current passed into the sample. Here we can see how the effect of the heat treatment on the current voltage relationship. Here the first one, the blue one, is of course the ACF as received without any treatment. 300 degrees C treated, 600 and 900. And of course you can see, for example, at 4 volts, by applying the 4 volt into the sample, we can see how dramatically the amount of current passing through the heat treated at 900 degrees. And more clearly, we can see the effect of temperature on the amount of current. And here, of course, as we increase the temperature, the amount of current increases. And of course, as we increase the amount of voltage, here 2.5 volts, we apply 2.5 volts between the electrode, and here we apply 4 volts. And of course, the effect of volt on the sample is, since we put the sample between 2 electrodes and apply the potential difference, so what we did is we inject electrons into the sample. So now the electron goes into the ACF and start to say, okay, now what I'm going to do? I have a breakage crystallite and I need to hop through that. So it's a little bit have a hindrance in movement, which of course creates the less conductivity, like I said in the beginning of ACF. But when we apply more voltage at 4 volts, now we increase the potential difference and the electron has to hop because I give them a push to move through the crystallite size and boundary. Next one. And by measuring the volume resistivity against the voltage, we can see, of course, ACF has 720 ohm per centimeter at 0.5 volt compared to about 120 kilo ohm per centimeter for the heat treated at 900 degrees. And of course, we see how drastically we decrease the volume resistivity just by doing the heat treatment. And here, this is a good representative of one of the new criteria we found on ACF, which is the charge-discharge effect. What I mean by that is, here, if we see the relationship between the current and time, we just put a fixed voltage between the electrode, and we measure the current with the time. Here, the time, the maximum time is 100 minutes, and we apply fixed voltage at 2.5. And we see here for the ACF, which is the as-received material, compared to the heat treated at 900 degrees C. We see like a very quick jump in the beginning and start to increase and level off, which is representative or similar to the criteria of charging of electron. The interesting criteria we found is at above 4 volts, here we measure at 5 volts, we discover a very interesting thing, which is the discharge effect, because I apply more potential and all the electrons are hop or move through the crystallite and charge. And as soon as I let the voltage be stable, here we have a discharge effect with time, because it's already the electrons jump or move at higher voltage. So we have charge and discharge voltage, and this criteria needs to be more studied, and that's what I'm doing now. By looking to the surface area, and like I said, this is the most important criteria and we need to keep it. So we have to study the surface area of ACF with the heat treatment. And here we can see the ACF without treatment or as received. We started with 1216, and at heat treated at 300 and 600 it increase, which is kind of expected, because like I said, we have an absorbent gas and water vapors into the pools of ACF, which obstruct the pools and surface area. It occupies some of the surface area. So by allowing the thermal treatment at 300 and 600 degrees, we get rid of the water vapor absorbent as well as some of the oxide absorbent into the pools. So we free some of the pools, and that's why when we measure the surface area, we get an increase, a little bit increase. But at 900 degrees, we get a little bit decrease. It's 1200. We just lost about 16 meters squared per gram, which is nothing compared to the total surface area. Next one, please. by measuring the pore volume, we have, like I said, two types of pores: the micropore, which is less than 2 nanometers, and the meso and macropore, which is higher than 2 nanometers. Of course, we like to have more. We like to have a big pore volume because it's more easier to fill these pores or to play with it as much as we can, instead of the smaller pores, which is less than 2 nanometers. And we also found a very interesting thing. We found that with the increase in the treatment temperature, we found that the micropores start to decrease, as well as the meso and macropores start to increase and level off, which is of course kind of expected, because the micropores start at higher temperature, start to collapse and connect it together. And that's why we moved from small pores to large pores, which is a good indication. Also, by measuring the X-ray, we didn't find any change in the crystallinity. So the ACF stayed as it is, amorphous, and we didn't gain any crystallite size. We didn't get increase in the crystallite size. Next one. Also, by looking into the scanning electron microscopy, we see here the cross section of the resistivity fiber is more or less circular. Compared here to the treated one at 900 degrees C, and the shape starts to be kidney shape. We lost the circular shape, and this is because like I said, some of the micropores start to collapse, and the shape of the cross section starts to adapt according to the collapsing in the micropores. Now, finally, the conclusion. We get a large decrease in the volume resistivity just with the heat treatment. In our subsequent papers, we did some type of composite material with the same ACF. But here, just as with the ACF and heat treatment, we get a decrease in the resistivity from 720 to 130 just with heat treated at 900 degrees for 30 minutes. We found the non-ohmic IV relationship. Also, we didn't lose we didn't lose much of the surface area, like I said. The total surface area and the amorphous structure were maintained through the heat treatment. We got increase in the mesopores and micropores, meso and macro, at the expenses of the micropore. So this one can be used as inclusion in the pore sizes of the ACF later. And like I said, of course, if we need to include anything into the pores, it's much easier to have a large pore than the small pore. So now you can transfer the ACF using this pore structure into a smarter material. We can dope it with any type of material we want and heat it, for example, at 900 degrees. We collapse the structure, and here we are. We have a micro electrode or a smarter material because we create the interfaces due to the inclusion. The properties imparted to ACF through the thermal treatment qualify ACF to be an excellent candidate material for an electrode in energy storage devices technology. And thank you for listening.
There is time for one question, please, and one question from the lady. I think we have time if you would like to ask from the last speaker. Yes, please.
The environment of the heat treatment. You have to speak in the microphone. The environment of the heat treatment will have a big impact on the effect of the heat treatment, because the carbon fiber will be oxidized around 600 degrees C, which you made the experiment. So whether you heat treated the carbon fiber under the inert gas atmosphere or the oxygen, the environment, you will have a different results. Do you have any experience in these aspects or any experimental results?
Could you please repeat your question again? I didn't follow it very well. You mean that I use the... You mean during the thermal treatment? I did the thermal treatment in a control atmosphere. I used the natural helium atmosphere, so there is no way for oxidation. I just do a thermal treatment.
Oh, I see. So,
Yeah. But the activation step that happens before I did the thermal treatment. The activation step is already done to transfer the carbon fiber to activate the carbon fiber, and it's a controlled oxidation step.
Okay, thank you.
Any more questions?
Ladies and gentlemen, you will agree that there have been very, very important papers in this session. And let's now thank the speakers. And I thank the audience, ladies and gentlemen, you have been so wonderful. And thank you very much for attending this session.